So today we're happy to have Thomas Massoni from Stanford. He's going to tell us about symplectic rigidity for Anosov laws.
All right, thank you very much for the introduction and for the invitation. It's always really great to be here. I want to talk about some kind of symplectic rigidity phenomenon for Anosov flows, in particular for orbit equivalences of Anosov flows, which is a natural relation around these flows. And before I forget, all I'm going to say is join with Jonathan Bowden. Okay, so to set the stage, I'm going to consider my playground is going to be a three-manifold. So all the usual adjectives. So I want it to be smooth, closed, connected, augmented. And oriented is going to be actually quite important. And I want to consider some dynamical systems on M of a sort of hyperbolic nature, and I'll be interested in Anosov flows. I will define them later, but for now, I just want to think of it as some kind of interesting hyperbolic types of flows that we studied for quite a long time. I mean, they're defined in more generality for also higher dimensional manifolds, but I will stick to third-dimensional because this is where the interaction between the topology and the dynamics and geometry of these flows is maybe the most striking. So these flows were introduced by Anosov, and originally I think people were studying geodesic flows on hyperbolic manifolds. And so a canonical example you can have in mind the geodesic flow on the unit tangent bundle of a surface sigma. So this is a hyperbolic. This is a type of Anosov flow. And actually, well, I was going to say recently, not so recently actually, but in the 90s, several people, so Mitsumatsu, also in Ashberg and Thurston, realized that those objects in dimension 3 are connected to symplectic and contact geometry. And so they have a particular construction of contact structures. For now, the flows, and actually you can do a little better. You can associate to such a flow phi. Maybe I need to add a few adjectives, but pretty much any another flow, it is possible to associate a Liouville structure on the thickening -1 cross M. So this Liouville structure, it's got the one form, lambda, so that the lambda is symplectic, and lambda restricts to contact forms on the two boundaries of -1 cross M and 1 cross M. And in particular, we have two contact structures, a positive contact structure, a negative contact structure on this manifold. So this is, I think, the construction of the Liouville structure itself is really due to Mitsumatsu, and Najberg Thurston mostly were interested in the contact structures. Right. Right. But then, of course, dynamicists like to consider the dynamical systems or the flows up to certain relations, and the natural equivalence relation for flows is orbit equivalence. So there are two flows, P and C. Let's say on the same manifold, they could be on different manifolds, but on M are orbit equivalent if there exists a homeomorphism H that standing the orbits. And when I say orbit, I don't mean necessarily closed orbit of phi. two oriented orbits. Oops. So, well, some people don't ask that they send orientation to orientation, but I will require this.
Preserves the order on each orbit?
Sorry?
Your H preserves the order on each orbit?
It preserves the orientation. It does not preserve the parametrization.
But it preserves which points come before which points.
This is what I mean by sending an oriented orbit to an oriented orbit. Not just
the
as
analysis is called orbit equivalence. That's monotone equivalence.
okay, I think some people say topological equivalence as well. I mean, there are lots of different definitions. Some people explicitly ask to have the orientation. Some people don't put it. I've seen different definitions. This is going to be my working definition for this talk. Apologies if this is not the usual one. Okay, but the important point is that it's a homeo. And for Anosov flows in general, this orbit equivalence is not going to be better than that. There is no theory that will allow you to raise this homeo to a C1 DFO, unfortunately. Otherwise, this talk would not exist. Okay, so now, of course, the natural question is, well, these Liouville structures, they really use certain smooth aspects of this flow, and if you apply some orbit equivalence, it's really not clear at all what happens to these symplectic invariants. You can't push forward or pull back a contact structure under a homeo. That's not defined. So the question is, if phi and psi are orbit equivalent, what can we say about their associated Liouville or even contact structures? So this is really the motivating question. And from these Liouville structures and contact structures, one can extract a ton of invariants coming from, for instance, Floer theory. Are these invariants meaningful to dynamicists, and namely, are they invariant under orbit equivalence? So the short answer is yes. Well, they're what about, sorry? The answer is they are the same. And the longer answer is the rest of the talk, essentially. Okay, but in particular, they have Anosov flows have well-defined symplectic invariants. And of course, the main difficulty is to deal with this homeo. We'll have to do a lot of things to this homeo to be able to deduce something from the Liouville structures. All right, so that was my introduction. So my plan is to first explain this construction essentially due to Mitsumatsu of these Liouville structures. So that's going to be the first part. Then I will carefully state the results, and if I have time, I will try to give some ideas of the proof, maybe some applications. So first, I want to review this what I call the Mitsumatsu construction, because it is really due to Mitsumatsu, even though the way I will present it is maybe just to Serena Hozoori, who sort of cleaned this construction a little bit, expanded it a little bit. So I'm just going to follow his construction. Okay, first I have to really tell you what an Anosov flow is and what I mean by that. So crash course in Anosov flows on three manifolds. Right. So I will write the definition here so that I can keep it for later. So a flow V is Anosov if it is generated by I could say C1 vector field, but for simplicity, I will say smooth vector field. A smooth, non-singular. Maybe I will say a smooth another flow is a smooth non-singular vector field. X such that. So I want it to be a hyperbolic type of flow, which means that I want to have some transverse direction where the flow expands exponentially fast and another direction where it contracts exponentially fast. So I have to be able to split my tangent bundle into this direction, expanding, contracting, and direction of the flow. There exists a phi invariant C0 splitting M, which is the line bundle called the strong stable bundle, direction of the flow, plus the strong and stable bundle. So ES and EU are C0 line bundles. Okay. And there is this, and there is also a metric and constants A, C, C prime. So that, and now I want to phrase the hyperbolic behavior and the exponential and contraction and expansion so that for every, so definition is a bit of a mouthful, but if I take a positive time and I take a vector in the unstable direction, if I measure the length of this unstable vector after applying the flow to time t, I want it to be bigger than some constant time exponential any time t, the size of the stable vector. And similarly, if I take a stable vector, same thing, but now it has to get smaller. And then maybe C prime, E minus A T, E S. Okay, and now hopefully I defined it correctly. All right, so let me just say that again because it's a lot. And smooth flow is Anosov if it's generated by a smooth vector field X, which is non-singular, no zeros, so that the tangent bundle splits in a phi invariant way into a sum of stable, unstable directions and the direction of the flow, so that if I apply the flow at some positive time t along the unstable direction, the length will grow exponentially fast. And if I apply it to the stable direction, the length decreases exponentially fast. All right? Okay. So thank you for now. And let me give you a few. Okay, so maybe I should say that E, S, EU, so presented for the strong, stable, and stable bundles. And there's a fact, it was actually due to Anosov himself, that those are uniquely integrable. Meaning that even though they are C0, they are tangent to well-defined line fields. And then we consider the weak, stable, weak, and stable, which is obtained by pairing the direction of the flow, etc. And those again are uniquely integrable, and they integrate to two-dimensional foliations. The weak stable and the weak unstable foliation. I will also ask that my flows are oriented, meaning that these stable and unstable directions have orientations. It's not always the case. You can always pass through double cover to achieve this, but I will add this. So a smooth oriented and nasal flow is always plus orientations for, I mean, only one has to be orientable because the other one will be, but for ES, okay. This is somewhat important. In particular, these two-dimensional foliations are oriented. Okay, so let me give you more facts. You might be worried about, and rightly so, you might be worried about the regularity of these objects. Well, it turns out that in 3D, Hasselblad showed that these weak, stable, and unstable bundles are actually C1. This is a little miracle happening in dimension 3. And this will make my life a little bit easier. Another fact is that these foliations are taut. So many different definitions of taut. Maybe the usual one is that you can find some transverse loop that intersects all the leaves, or maybe you want through every point to have some transverse loop. Pick your favorite definition, but in particular, they have no contractible transverse loops. That's to know. I mean, in this context, maybe easier thing to do. Another thing I should say to maybe highlight the fact that these flows can be thought of as topological objects. They are structurally stable. What does it mean? If you modify this vector field X with a small C1 perturbation, well, it still generates an Anosov flow. And the new Anosov flow is actually orbit equivalent to the old one. So if you know gray stability for contact structures, it has the same flavor. Okay. Lots of other interesting facts about Anosov flows, but maybe I will stop here for now. There is another one that I'm going to use in a second, which is that here I just said, oh, there exists some metric. Actually, you can replace it. There exists with for every. But there are better ones, and the metrics that are called adapted, for which these constants C and C prime are 1. It means that when you apply the differential of the flow, you immediately increase or immediately decrease. So resistant matrix, so it means C prime is 1. That's a classical fact. All right, so like the classical theory for another flow, but then because we want to do contact and geometry, maybe it's better to think about these objects in terms of forms, differential forms. And so I kind of want to dualize everything. And I want to, okay, so if I dualize, I don't want to give too much details about this, but there exist one forms, well, C1, one form, alpha U and alpha S, such that the following properties hold. So the kernel of alpha U is the stable bundle, we dualized, so I have to inverse the letters. The kernel of alpha S is weak unstable bundle. In particular, the vector field X is tangent to both of them. But then because these bundles are invariant into the flow, if I take the Lie derivative of alpha u along x, I should get a multiple of alpha u with RU. And if I do the same thing with alpha s, I get RS alpha s. Where so RS and U are just functions to R, which can be assumed to be C1. It's not immediately clear that they can be assumed to be C1, but it's possible to find such one forms. And okay, so how to get those? Well, we take some vectors spanning EU and ES, and then do some duality. And if you pick unit vectors spanning the strong stable and unstable for an adapted metric, you will get that these coefficients satisfy that RS is negative and RU is positive. So these RU and RS are called the expansion rates, and they correspond exactly to the best constant A that you can pick here or there for some adapted metric. And the fact that the flow is Anosov exactly means that RS is negative, you immediately exponentially contract in the stable direction, and RU is positive, you immediately expand in the unstable direction. Right. So I will call such a pair. So here I'm saying that there exist these forms, and I call that a defining pair for my Anosov flow, and this is really the key quality. And so maybe I should attribute in this form. At least I learned that from Hozoori. Okay, so well, maybe I should give you some examples of Anosov flow. So I already gave you one, which is the hyperbolic flow. Actually, there is a way to understand the geodesic flow of the hyperbolic surface. Well, you know, the unit tangent or cotangent model of the hyperbolic surface, you can lift it to the universal cover. So really, you can work on the unit tangent or cotangent model of the upper hyperbolic plane, the upper half plane, and then you can write the geodesic flow. You know, you can identify this thing with a PSL2R, and you can write matrices and identify the geodesic flow by acting by a certain matrix in the Lie algebra SL2R and etc. There is an algebraic way of formulating this. And my other favorite example is the one of the suspension of a diffeomorphism of the torus. So if you pick a matrix with coefficients in Z that is hyperbolic, so the trace, let's say the trace is strictly bigger than 2, this acts on R2 mod Z2, so on the torus, and you can do the suspension of this thing, get a 3-manifold, and the suspension flow is also Anosov. Okay, so that's the other prototypical example that is also algebraic in nature. And in those algebraic examples, everything, all these data, all these alpha U, alpha S, and etc. are all smooth because just do algebra. But in general, it's not. So in general, you have to worry a little bit about the smoothness of the objects, but anyway, let's not worry about this for now. Any questions? All right, so now I can actually write down this Mitsumatsu dual structure. Well, maybe first I can tell you about the contact structures. So, and here I should maybe draw a picture. Here. Maybe colors for that. So, right. I will draw a picture in the transverse direction to the flow. So the flow X is pointing towards you, child. And then I have two green direction. I have a stable green direction where things contract, and then I have a unstable direction where things expand. And if I try to draw the the dynamics nearby, it looks like something hyperbolic, it looks like a static. But now, what if I take some bisectors of these stable and unstable directions? So I can pick a bisector like this. And now we see that if we flow this bisector along the flow, what happens is that it gets pushed along the flow, and so it will twist along the flow. Okay. What is a plane field tangent to a flow that twists along the flow? That's called a contact structure. So with this construction, I get xc plus here, and similarly, I can do the same with the other. Of course, I should really be more careful about orientations. What is positive, what is negative, but trust me, this is the correct orientation. Or maybe it's the other, who knows. But if I do this other operation, I will get a plane field that will twist the other way along my vector field, and that will be a negative. Does the picture make sense? Vaguely? Yes.
Doesn't it like approach the red?
Yes, it will. This will be important. Yeah, thank you.
What's the question?
If it approaches the red. Yes, if you fall for a very long time, xc plus will get very, very close to the red. Xc minus as well. But if you fall for a very negative time, you will approach the other one. So you can and you should think of these contact structures as secretly approximations of the weak stable and weak unstable, modulo flowing them for a very long positive or negative time. And this is actually the key. All I'm saying about the Anosov flows can be generalized to some extent to certain taut foliations. And here the taut foliations are the weak stable and weak unstable. So I'm just being lazy and presenting what we proved in a sort of simplified case. But really the important property is that those will approach those given foliation. Yeah. Okay, so if you're not convinced by this picture, maybe you will be convinced by some formulas. So what I can do is that I can define alpha plus to be stay careful about the signs. Alpha u minus alpha s, and alpha minus to be alpha u plus alpha s. And now if you use these relations that I wrote here, you use Cartan magic formula and all that, you can check that alpha minus and alpha plus are a negative positive contact. I play with just C1, but that's fine, we can smooth them. So that makes sense. Right. Actually, if you do a bit more computations, you will see that the rate vector fields of alpha plus and alpha minus are transverse to these foliations in the correct way. So I think that the rate vector field for C plus is roughly pointing this way, and the rate for C minus is roughly pointing that way. That is again some computations. R minus plus are transverse to weak stable, unstable, or taut, and so in particular, these rep flows don't have contractible closed orbits.
Was the hypertight?
Yes. Yeah. So this, I should say that C plus minus, which is the kernel of alpha plus minus, are hypertight. All right. By construction. Now, if you want to cook up a Liouville structure on the thickening, yes.
So is there data of the stable and unstable? Like, is it part of the, like, is the data part of the Anosov flow, or it's a...
So these bundles are intrinsically defined. Once you know that they exist, they're uniquely characterized, pretty much. Well, maybe not the strong ones, you have to be careful, but the weak ones definitely are. Here I'm choosing forms alpha u and alpha s. And smoothings also. I wrote some papers some time ago showing that these choices don't matter. But what I will do next will also show that they don't matter. So yeah, no need to worry too much about that. All right. So now I'm just going to do the simplest thing ever, which is that I'm going to interpolate between these two contact forms on the thickening. So 1 minus 1 cross m, where t is the variable in the direction, let lambda to be t minus 1 alpha minus plus, I have to think, plus 1 plus t, nope, 1 plus t alpha plus. Does that work? Yes, maybe I'll just write the t plus 1. This is not what happened to write. No, that's fine. Okay, yes. So this formula, so this is a one form on this thickening, and you can check that lambda is Liouville. Well, we already know that it restricts to alpha plus and alpha minus, well, to alpha plus to alpha minus in the boundaries. That's good. So the only thing to check is that d lambda is non-degenerate. And again, you unpack the definition, you write alpha u alpha s, you use these formulas and etc. You will get that it's non-degenerate. You'll be slightly worried that d lambda is just C0, but if you smooth lambda a little bit, then you're good. So
could you explain that picture again?
yes. In this picture, I have these two invariant directions, the stable and unstable. If I take some plane field that contains the flow and that is sort of a bisector of those, because of the nearby dynamics near the orbit passing through this point, the dynamics will sort of push this plane field closer to this line. But so, if this is the flow line, what are the flow lines nearby? Well, if I take a flow line that is a bit here, there will one component that will get closer here and the other component that will go further away. And so I will see dynamics that does this. In particular, if you flow objects along this, they will get closer to there. So this plane field will, after flowing, will tend to twist and get closer to this red direction. If you think about what the contact condition means in dimension 3, and this is also a place where I use dimension 3 crucially, well, if you have a plane field containing a vector field, and if you flow this plane field along the vector field and you get something that twists strictly, that is equivalent to the contact condition. If it's invariant, it's sort of equivalent to being a foliation, if it's smooth enough. Okay. But if you left in this picture, you can just write the equations. But yeah, plane field that twists, that's, for me, that's all right. And well, okay, there are many interesting things that I could say about these Liouville manifolds. Schematically, they will look like this. So it's interval M. And if I look at the Liouville flow, defined by this Liouville structure, the Liouville flow is tangent to 0 cross M. And if I move away from it, the Liouville flow will be transverse to these slices and eventually be transverse to downwards. Interestingly, the skeleton, if you know what it is, well, which is what you obtain by flowing backwards in time for a very long time, the skeleton is exactly going to be the 0 cross M. That's a dimension 3 skeleton in a 4-dimensional Liouville manifold. That's a big skeleton. Usually, maybe we expect a half-dimensional skeleton. And in particular, about these manifolds are not Weinstein. You can't build them by attaching symplectic handles because, well, the third homology is non-vanishing, for instance. So those are pretty different from what symplecticians usually consider for Liouville manifold. In particular, a lot of the techniques that are known don't work for those. So anyway, so that's the construction. And now there are no questions. I will try to write some theorems. And again, we have more general results for suitable taut foliations, but I'm just going to state it for Anosov flows because it's easier and I think it's already interesting enough. Okay, so set theorem A is the following. Okay, so I want to say that if I have two Anosov flows, they're orbit equivalent, then their Liouville structures are the same. So P, let's say phi0, P1, oriented Anosov flows on M, and oriented means that the weak, well, let's just say the weak stable and weak and stable bundles are oriented. And H, the, I will say oriented, orbit equivalence. So an orbit equivalence will always send the leaves of the weak stable foliation of the first Anosov flow to the leaves of the weak stable foliation of the other Anosov flow. So that's because there is an intrinsic way, purely topological way of characterizing the weak stable and weak unstable foliations by 2 points are in the same stable leaf if when you flow them for a very long time, they will get closer and closer together. And if you take all the points that satisfy this property, that will actually define a weak stable leaf. And this is really topological, so if you pass to a homeomorphism, this is preserved, and so automatically the orbit equivalent will send weak stable to weak stable and weak unstable to weak unstable. Not the strong ones a priori, but the weak ones, yes. And I will say that this orbit equivalent is oriented if it also preserves the orientations on these weak stable and weak unstable. If it does not, then you just tweak the orientations. If you tweak the orientations, you might change the Liouville structure in a controlled way, but maybe you will replace alpha plus with minus, alpha plus, alpha minus with minus, alpha minus. There is some co-orientation business. I won't bore you with all this orientation nonsense because I actually don't remember anything about it. I figured it out at some point and then I immediately forgot it. Anyway, I have two Anosov flows and oriented orbit equivalence between them. Then I'm going to have lambda sub phi0 and lambda sub phi1. The associated Liouville structures through these constructions, those are the same, meaning that they are exact, symplectomorphic. And this means that there exists a smooth Liouville cross M such that the pullback of lambda phi1 is lambda phi0, potentially plus some df, where f is some smooth function that we can assume to be supported away from the boundary. So that's the notion of extensibility. Does that make sense? In particular, the contact structures at the boundaries are also contactomorphic. But potentially, if I had two different contactomorphisms, which are coming from the restriction of this phi to minus 1 cross m and 1 cross m, they might not be the same. In particular, C0 plus minus is contactomorphic to C1 plus minus, but not necessarily via the same contact morphism.
So what was the last one you were told?
Contact to and new for morphism. So nice. All right. So in particular, all these symplectic invariants that you can attach to those Liouville structures are attached to the oriented orbit equivalence class of these flows. But there is a slightly different perspective that you can see where, okay, maybe you don't really care about the Liouville structure, but you care about the contact structures. And it turns out that, well, maybe I should look at this. Which is that these two contact structures, C plus and C minus, they are a bit special because they are transverse and they exactly intersect along the flow. Okay, so, where do I write this? And note.
So you said df can be 0 near the boundary.
Yeah.
So, okay. So then the restriction of phi to that boundary and that boundary is maps one contact structure
Yes.
to this.
Yes. Yeah, and so zero. Might not be able to achieve f as the same value. I'm not sure. Probably not. So here I just wanted to say that C minus is next to C plus, and usually a pair of oppositely oriented contact structures is called a bicontact structure. So guys. Okay, but now you might also ask me, what happens to the bicontact structure themselves? Let's forget about the Liouville structure. I don't care about this. I care about the bicontact structures. Because what I wrote here, and in particular, this part does not tell you anything about the pair itself. It just says something about the contact structures independently of each other. Okay, well, we have a theorem for that. And B, like bicontact, that says that so under the same after this, these two bicontact structures for phi naught and the one for are deformation equivalent. Which means that first you apply a diffeomorphism to the pair, and then you apply a homotopy of bicontact structures. That makes sense? So I have this bicontact structure for phi0, this bicontact structure for phi1. I want to push this thing along the orbit equivalence. I can't because it's just a homeo, but I can smooth that thing, apply a smoothing. I don't quite get the bicontact structure for phi1, but I get something that is homotopic through bicontact structures to the one for phi1. Well, it turns out that, and this again follows Mitsumatsu and Thurston, the flow inside of a bicontact structure, a priori, if I just take a bicontact structure, the flow inside is not necessarily Anosov. Anosov flows give rise to bicontact structures, but a bicontact structure usually gives rise to what's called a projectively or conformally Anosov flow. you sort of take the definition of Anosov, but you don't require a strict expansion and a strict contraction. You just require that there is a direction where it expands more than a direction where it contracts. But you're not asking the contracting direction to contract and the expanding direction to expand. There's one direction that expands more than the other. That's called projectively or informally. So an immediate corollary of this result is that orbit equivalent Anosov flows are deformation equivalent through projectively Anosov flows. Deformation equivalent projectively.
This deformation equivalence is in terms of the contact by contact structure on the count.
Sorry?
This deformation equivalent is in terms of that definition, the contact.
Yes, yeah, it's the same. So you first apply a diffeomorphism and then you have a path.
Of contact by contact structure.
Yes. And back contact structures are essentially the same to contractible choices as projectively Anosov flows. So this is because there is this quest models. Provided that everything is orientable and oriented in the correct way. All right. So before I try to explain something about the proofs, also, are there more questions about the statements?
So
Yes.
could you just start with projectively Anosov at the beginning instead of Anosov?
No, unfortunately. So first of all, projectively Anosov flows don't necessarily have invariant foliations. They have invariant bundles, but they might not integrate to foliations. And even if they do, these foliations would not be C1. And it's quite crucial in these theorems that the weak stable and weak unstable foliations of Anosov flows are C1. But then there are also further properties like the tautness of these foliations, which is important. So there are various places where it would be interesting to try to say something more general for more general projectively Anosov flows, but I mean, I can cook up a statement with imposing sufficiently many conditions on those projectively Anosov flows, but yeah, it's not clear that this rigidity actually holds for those. And projectively Anosov flows, so they have these bicontact structures, they might not have this dual structure. Yeah, for those, I don't know. Yes.
So what invariants can you compute for these dual manifolds? Recipe in terms of the contact structures.
I personally cannot compute much. Well, okay, I wrote a paper with Kai Silibag, Agustin Moreno, and Oleg Lazarev a few years ago where we computed things for the easiest examples, where it's easy enough to compute certain things. We looked a bit at the Fukaya category of these guys, and we saw that it's weird. And that's pretty much what is known so far, unfortunately. So, okay, one interesting thing is that the closed orbit of the Anosov flow times the interval, they naturally give rise to exact Lagrangians in this trivial manifold. Okay, so you have exact Lagrangians, you want to look at the Fukaya category generated by those. We try to apply a Bouzet's criterion to see if they generate the Fukaya category. They don't seem to, at least a Bouzet's criterion doesn't work. This subcategory is pretty wild. Maybe there are other mysterious Lagrangians that you don't see. It's pretty open so far. Anyway, that's the topic of a different book. Okay, so let me ask two questions which, well, one is question A. Is the converse to theorem A true? So if lambda phi 0 is exact symplectomorphic to lambda phi1 are phi0 and phi1 or equivalent. In general, I don't know. In some cases, I do. And question B, if phi0 and phi1, and this question I learned it also from Hozoori, if phi0 and phi1 are deformation equivalent, even homotopic, prove projectively an Anosov flow. They
I said.
will be equivalent as well. So is it possible to tell Anosov flows apart using individual structures or using these bicontact structures? That would be great. That would be really amazing. For instance,
What do you expect?
I hope it's true, at least for transitive flows. But I don't know how to prove it in general. So there is a big question in Anosov theory that I didn't mention earlier, but it is expected that every free manifold has finally many Anosov flows up to orbit equivalence. Actually, even finally many projectively for pseudo Anosov flows, but let's just say Anosov flows. So this is open. What is known, though, is that there are finally many tight contact structures with vanishing zero torsion, which is the case for those. So the candidates for Xc plus Xc minus are in finite number up to isotopy. But now the question is somehow how, if you have Xc plus Xc minus, how many ways do you have to assemble them to build some Anosov flow? If you have finally many ways, then you prove the finiteness. But yeah, that is not. So those somehow could think of those as maybe steps towards proving finiteness, if those things are true. I have some ideas, but those are questions, not conjectures. So don't hold me accountable. There is a class of selection in simple Anosov flows called arm-covered Anosov flows, for which those questions are, well, the answer is yes. Sort of for, not for silly reasons, for important reasons, but for those essentially just Xc plus or just Xc minus determines the flow. But okay, that's a, maybe I won't say too much about those, and I will try to say something. So the proof essentially has 3 steps. 2 hard steps and 1 easy step, I would say. The first step is that, okay, you're given an orbit equivalent, you're given a homeo. What can you do with this? It's not good enough, so you have to upgrade it to a ditheo. Of course, every homeo on a free manifold can be approximated by a ditheo, but you don't want to do it arbitrarily because you might completely destroy all the structures, all the invariant bundles. So the first step is to find a careful approximation of orbit equivalence. And okay, I will state this for another flows, but again, there is a statement for foliations, which is actually fairly general. So theorem 1 is the following. So okay, I've erased the setup, but it's the phi0, phi1, h as before. Okay, so for every epsilon, there exists an h epsilon, smooth. Epsilon goes to h in C0, and such that it sends the weak stable of phi0 fairly close to the weak stable of phi1, and the weak unstable of phi0 fairly close to the weak unstable of phi1. So, so if I look at H epsilon and I push forward weak stable of phi0, and I measure some distance. So there is some metric in the background that is always specified. Then I can do the same thing with weak stable distance. So there is this very careful approximation of the homeo into some smooth DFO that does not move the weak stable and weak unstable too far. So the key points are that, well, as I said, the foliations of 0 or 1 are small. So I can pick C1 charts in which they are flat. That's very important. And then, H says F0 weak, stable, weak, and stable. F1 stable, weak, and stable. So this is a kind of like a foliated, bifoliated homomorphism. Because those guys are C1, I can pick C1 charts where they're standard, and then I can represent my orbit equivalence locally. Okay, now you have a function and you sort of want to approximate this function smoothly. So it's locally easy. Because it essentially amounts to approximating continuous, strictly increasing functions by smooth ones with positive derivatives. Okay, I think we all know how to do this. So locally, it's fine. The difficulty is to do that globally. To do that globally, maybe you want to triangulate the manifold. You want to do that near the vertices, and then extend your approximation near the edges, and then extend the approximation over the two faces, and there it gets tricky because you've already messed up things, so you have to connect them carefully, etc., while keeping these everything close. So there's an inductive argument, and at each step you have to be really careful about that. Yeah. Okay. So that's step one. So of course it's easy to tell the idea. Writing it down is much more tricky, but it works. Second step is also quite technical, and it has something to do about the uniqueness of contact approximations to foliations. So there is a deep theorem of Thomas Vogel that says that for nice C2 foliations, I won't tell you what nice really means here, but okay. Another foliations are not C2, they're C1, but let's just pretend. Those would be nice. Then contact approximation are unique. What does it mean? I'm just going to draw a picture. In the space of plane fields, here I have TF, my original foliation. Vogel constructs some neighborhood, some C0 neighborhood of TF, so that if you pick two contact structures, say positive contact structures, C0 and C1, in this neighborhood, then these two contact structures are homotopic as contact structures via some homotopy that can be pretty wild. So you can really go out of this neighborhood, go very far away. So they are the same contact structure, but they don't stay close to TF. Okay. Well, if they stay close to TF, then that would be very great because we wouldn't have to do anything, but we did have to do something. We had to upgrade this statement We don't show that we can stay close to TF. That's actually very tricky. We don't really need that. So the theorem is, so I just need one Anosov flow. So let's say phi Anosov also oriented F is the weak stable foliation, say. And let Z be some smooth transverse vector field. So I fix a transversal. And now I will say that my contact approximations are unique through contact structures that stay transverse to the Z. Sounds like it's not much of an improvement, but actually it's very important improvement for us. So then there exists a neighborhood of TF. So it's a C0 neighborhood of TF, such that any two C0, C1, and V are homotopic through contact structures transverse to, and this is really the part where you have to sweat a little bit. And also the fact that these Anosov foliations are not C2, they're C1, that's not the worst part. The worst part is to really go through Vogel's proof and be ultra careful to stay transverse, and there are some steps in the proof where we had to actually do something more to achieve that. Okay, so in my last minute or so, I will tell you how to put these things together with some kind of dance. We'll see how it goes. So phi 0 here, I have phi 1 there. Let's just say the sort of okay, so I have my C0 minus C0 plus here. I bring them very, very, very close to the foliation for the weak stable, let's say. I apply a small smoothing of H. When I push it, I get new contact structures that are very close to the weak stable. And now I want to use this uniqueness. What is Z? Well, I can take Z to be dual to one of these alpha U or alpha S, essentially, or D alpha U, D alpha S. So the important point is that the weak stable foliation has some exact two-form positive on its leaves, namely D alpha S. Well, it's not smooth, but you can smooth it. Okay, then I can dualize to get a vector field. This exact two-form positive leaves is really the ingredient that we need to get beyond the contact structures and get the Liouville structure. Okay. So if you do this, you do some algebra, what you would get is not quite a path of Liouville structures yet. You get something a bit weaker than this, that I call pre-Liouville structure. What is it? Well, we have a path of contact structures, C plus and C minus, and we have a path of one forms, so that D of these one forms are symplectic, but they might not restrict to contact structures. I just know that D lambda it dominates C plus and C minus in the boundaries. So it's an exact weak symplectic filling. So I have a path of exactly symplectic fillings of these guys. Then there is a way using arguments of Eliashberg dating from the 80s and 90s of upgrading this guy to a path of actually Liouville structures. We do have to do pretty wild deformations in this step and also in the last step. So I don't really know what this path of Liouville structures eventually end up being. The only thing I know is that this exact symplectomorphism that I wrote earlier is topologically isotopic to identity cross the orbit equivalence, because it's obtained by perturbing this orbit equivalence and then doing some isotopies. But that's pretty much the only thing I know. Well, sorry for rushing the end. I think that's what I would say.
Let's see. Do you have any questions to Thomas?
So what's missing going backwards?
For which they
No, I mean, when I asked you the question before, you said
Yeah.
if they are equivalent on that side, then maybe you can say something about the flow.
Yes. So one idea when the two Liouville structures are exactly symplectomorphic would be to look at the skeleton. So in this construction, as I said, the skeleton is this codimension 1 copy of M, and the Liouville flow restricts to the skeleton and is essentially a rescaling of the Anosov flow itself. So now the question can be rephrased. You just pick one Anosov flow, you do the construction, you add some dF to it, so that the new skeleton is also some codimension 1 thing, and the new Liouville is tangent to the skeleton and Anosov. And now I want to relate these two.
So the problem is that the
Yes. Yeah. I mean, yeah, the universal problem in understanding these homotopies of Liouville things is trying to understand this dF, and a priori, you're given a dF, you don't know what it looks like, but you have properties of very strong properties of the skeleton. And so if you are able to relate the orbits of the new skeleton to the original one, you're in good shape, because Anosov flows are pretty much classified by their homotopic, free homotopic classes of closed orbits. There's like some big theorems of Bakame, mine, also Pelney, I suppose, at least for transitive flows. And so if you are able to relate these two dynamics, to relate the closed orbits, then you're in good shape. But yeah, this is something I don't quite know. I mean, maybe one first step would be to say, well, as I told you, you take a closed orbit, you take the product with the interval direction, you get a Lagrangian. So now you would also get some Lagrangian cylinder that can have some very complicated topology inside of this manifold. You can make it intersect the skeleton transversally. Can you relate it to some orbit of the original skeleton? No. That would be sorry. For the bicontact structure part, the goal would be to maybe try to keep track of what the foliations are, or maybe the, okay, I said projectively Anosov flows don't have invariant foliations. They don't, but they have invariant branching foliations, which are almost good enough. And so here the strategy would be to try to, when we have this path of projectively Anosov, starting and ending in Anosov, going to see if these foliation or these branching foliations still remember something dynamical from the first one to the second one. And the hope would be to maybe say that, to like build some, maybe an orbit equivalence would be like a semi-conjugacy. And for Anosov flows, if one is semi-conjugate, I mean, semi-conjugacy is very, very strong for Anosov flows. So if you know that they're semi-conjugate in both ways, they're essentially. So that would be analyzing these branching foliations that appear and trying to see if there are some dynamical properties that subsist. And there are some recent work of Raphael Potry and Sergio Fenley that sort of prove some kind of dichotomy of what these foliations can be. I mean, there are some, but anyway, it's technical and I don't really understand it that much, but that would be a natural strategy that actually Raphael Potry told me, and yeah, it's plausible.
You have more questions? Some basic questions.
Yeah.
So you're approximating this orbit equivalence with things that almost fix E0, or?
Yeah, it's you have a pair of transverse foliations here, a pair of transverse foliations there. The smoothing is going to send these pair of foliations very close to this pair of foliation.
Oh, yes.
So you want to use these foliations to guide you in the approximation.
But so if you, sorry, a very, very basic question. But if you have an orbit equivalence, then that already fixes the foliation, like on the nose. Sorry, it maps one.
Yes. Yes, it does. But that doesn't mean that it's smooth. It just means that it sends something C1 to something C1. But the hard part is to modify it in transverse direction.
Why does this?
Sorry?
Can you say like a word on why that's true? Why like it's so
Yeah, so let's do a 2D example. And so I have this foliation, and now I have H. Okay. So this foliation is just, horizontal and horizontal. So what does H look like? H of xy is of the form A of xy, B of y. Okay. It sends something of a height y to something of a height B of y. And the first component is just move. The conditions here is that B is strictly increasing, and if you fix A of something y is also strictly increasing. Okay. Well, now it's very easy to approximate this guy with the smooth one, still preserving those foliations. You approximate B by something smooth with positive derivative, and you approximate this family of strictly increasing continuous functions by a smooth family of smooth functions with positive derivative. But this only works locally. The problem arises when you start doing things where you did things near some one skeleton, and now you want to fill this homeo there. Well, maybe this ETH here was sent here, but maybe this corresponding leaf here was sent there. So you're sort of forced to send this guy to this guy. Now you modify the foliation on the target. You want to make sure that you don't modify it too much. Of course, if this one and this one are very, very close, then this kind of silly interpolation will be C1 small. So at the previous step, you had to approximate it very, very, very well, so that at a later step, you approximate well enough, and so that for a carefully chosen cutoff, the C1 thing is not too bad. That's the toy model of the argument. Now you have to actually write it down and write it down in 3D, and yeah, but that's essentially the gist of the argument.
Okay, more questions? If not, then let's say the colors.